Hi guys, welcome to our channel of Sciences and Mathematics. Today we are going to look at a concept in enthalpy, and this is the concept of enthalpy formation. Now, when chemical substances or species interact with one another, it may result in the formation of a product, maybe which is we refer to as a product. Now, in this case, we have looked at some of the examples that we have talked about in some of our videos, that maybe some chemical reactions or chemical reactions specifically are defined by the valency electrons of elements, whereby we find that some of the elements prefer to bond covalently with others to form stability, while others prefer to form maybe ionic compounds, etc. So in this case, we are going to see that the concept of bond formation bears a very significant role in trying to discuss the enthalpy of formation, and we're going to use maybe a specific example to try and illustrate how we can be able to describe this concept of enthalpy formation when chemical reactions are taking place. So without further ado, thank you and welcome. So our topic of discussion for today is enthalpy of formation. So the enthalpy of formation comes from the concept that I've mentioned about formation of new products when a chemical reaction is taking place. So still we are just going to use our normal illustration for a chemical process whereby the reactants react to form product. Now in between there are some of the reactions which may not occur just generally as we have illustrated, whereby maybe some will require some kind of a heat or energy to be provided, maybe in form of like a natural process for formation of food in plants, that is photosynthesis, requires the concept of light energy. So therefore, there are some of the chemical reactions that might require heat or light energy in order for them to proceed. For instance, we had used the concept of burning of methane to illustrate how we can be able to give a notation for enthalpy. So this is going to form a CO2 plus water, so stoichiometry. So this is a gas. So therefore, in this chemical reaction, we find that this chemical reaction does not take place just the way we have just illustrated, but it will require some energy to start. After that, the chemical process will just proceed even without further application of energy. And of course, we are going to see that, especially when this is a form of fuel, whenever we are trying to perform this particular kind of a reaction, it's normally going to be a spark or maybe a form of energy which is going to initiate the process of burning in order to ensure that the process goes on continuously. Now, as soon as that process begins, then large amount of heat is going to be released. So therefore, we're going to have a negative sign there to show that the heat is released from the system to the surrounding. Now, in this case, we're also going to see that if we try to do a reaction between methane and chlorine to form chloromethane, this process is going to be very slow if it is done in darkness. Basically, if it is done in darkness, the process is going to be very slow. But if some light is introduced, or maybe in the presence of sunlight, the process is going to be violent, or maybe a violent reaction is going to occur in formation of a chloromethane. Maybe still illustrate CH or maybe Cl form tetra. So in this case, basically I'm just going to leave it at this. I'm not going to illustrate how that chain reaction goes on. But the main concept I'm trying to illustrate is that in those two particular scenarios for darkness and sunlight, the reaction becomes violent, or it occurs violently in the presence of sunlight, basically, which indicates that it needs energy in order for it to proceed. So in forming some of the products, we'll find that there is some of the energy which is injected into the system in order to initiate these processes which are taking place. And when we were trying to talk about introduction to organic chemistry, we said that carbon prefers to bond covalently with other compounds to form maybe long chain carbons, or maybe other compounds when it bonds with other atoms apart from carbon itself. So in this case, still that concept is applicable, whereby we find that across the periodic table, there are some of the elements which we prefer to bond covalently instead of maybe losing or gaining electrons. Gaining electrons. And there are some of the elements which are in between, like carbon, sulfur, oxygen, phosphorus, perhaps nitrogen, which are in between here. So those particular kind of or species of atoms will prefer to do a covalent bonding with other elements in order to form stable compounds instead of either losing or gaining electrons. So in this case, when these compounds have been formed, you find, for instance, a substance like methane it is structure illustrated as such. So the overlap of these specific orbitals for carbon and hydrogen forms a hydrogen-carbon bond. So this bond formation is a process that entails either the absorption or release of energy, but basically we are going to see how we can be able to describe either breaking or maybe formation of a bond in terms of the endothermic or exothermic reactions that we talked about. Now, in this case, we're going to give a specific example and try to see how we can be able to illustrate that, of course, using the example that we had already discussed about. So let me just do that using an illustration. So in this concept of enthalpy formation, it basically deals with the concept of bonds and overall the energy which is involved in either bond breaking or bond formation of products during a chemical reaction. So as we have illustrated using the methane reaction with the chlorine, we're going to see that this methane can be illustrated using this one. So this is just an illustration, not a product. If it is illustrated using this and there's a substitution for chlorine at that specific point, then we are going to have chloromethane. So in this case, the hydrogen has been substituted, which implies the carbon-hydrogen bond has been broken while there is a formation of a chlorine-carbon bond. Maybe you can use those illustrations to try and put an emphasis on that. So there's a breakage of this particular bond where there's a formation of another bond. So these two processes entail energy because there's a lot of energy that is used to hold this covalent bond together. And in the formation of this energy, this particular case, we are going to have the breaking of bond, whereby this one will be an endothermic process. So the chemical reaction will take in heat from the surrounding into the system to assist in breaking of energy. When we are trying to talk about the concept of changing of phases from solid liquids to gases through increase in temperature, the increase in temperature was the taking of heat from the surrounding into the system to enable the ice or the molecules of the ice to break away and form liquids. So the breaking of bonds entails the concept of endothermic energy, where the formation of bond is exothermic energy. So this is a release of heat to the surrounding. Now going back to the illustration that we have given for methane and chlorine, we will see that the methane is a molecular compound that is made up of carbon and hydrogen, which are held together by strong covalent bonds, as I've already mentioned. So the chlorine, which is existing as a diatomic molecule, we find that the strong covalent bonds which exist between those chlorine atoms are broken first to give free or separate species, as I can say, maybe entities, before they join together to form products in this case. So in the same way, we are going to see that the carbon-hydrogen bonds will be broken. And this, of course, as I've illustrated, for the breakage of bonds requires energy. And the formation of bonds, of course, will entail the concept of rearrangement of the molecular structure of that particular species, and it will entail the concept of exothermic energy by releasing of heat. Now, the energy spent in breaking the bonds in methane and chlorine molecules is less than the energy required when the products are formed. So as we said, we can be able to illustrate the energy formation, or maybe which is either taken in or away from the system, using energy level diagram. Now, for the overall reaction of methane and chlorine, we can be able to illustrate that maybe using a general reaction, a general stoichiometric reaction, which I'm going to just illustrate shortly. So I'll just go away this so that we can have that space. So I'm going to write that equation for the reaction between methane and chlorine still, so that we can be able to use it for our example. So we're going to have tetrachloromethane plus hydrochloric hydrogen chloride. Maybe we can just have a look at this, and this is how many? 4 plus 4, 8, 4, 8, hydrogen 4. Okay, we have balanced that equation. So in this case, in representing this particular equation in form of an energy level diagram, we're going to have energy in kilojoules, and that scale against the reaction path. For us to represent the enthalpy of formation of this particular product. So this is energy in kilojoules. Therefore, you will see that the reactants are going to have a lower energy when they are reacting. So we are going to have CH4 plus 4Cl2. They're going to take in energy for that breakage of bonds, and we shall of course form separate entity for carbon plus hydrogen plus 8 chlorine. So that process occurs before this is basically the process of rearrangement of different species for this particular product, and we're going to see that this is the energy that is absorbed or taken in to break the bonds. So therefore, when the product is formed, we're going to see that it's going to have an exothermic reaction, that is a bond formation. And for the product, that is a tetrachloromethane, so we are going to have a C4 plus 4HCl. So that's the product that is going to be formed. So basically, these are reactants, and this is our product. And if you try to look at this specific graph, suppose we had just figures to indicate this. The net change in enthalpy, of course, is going to be illustrated using that particular difference that I've indicated there, which is a line with dotted. Of course, this is not just exact, but just for illustration purposes, you can find that the reactants are reacting to produce a product, and the net change in energy is going to be, of course, still a negative delta, which is going to be illustrated as such. Now, as we mentioned, the reaction which is taking place like this, that involve the concept of sunlight, or maybe taking another form of energy into the system to initiate the process, that kind of energy is referred to as activation energy. Activation energy. So basically, this is the energy that is required to initiate a chemical process or maybe a reaction. And we are also going to see in some areas maybe where we can be able to generally represent the activation energy, perhaps using this kind of an illustration in between there. But we'll deal with that when we come specifically to that concept. Now, I had given an example of a formation of ammonia using this reaction. So in thermochemistry, we're going to see that whenever you are trying to reverse a reaction, the net change in enthalpy is going to be of a negative value, or maybe of an opposite value. For example, if we have a formation of ammonia, so this is 2 here, 3. So if we have formation of ammonia and the net change in, or maybe the change in enthalpy is going to be negative 92.8 kilojoules. If I reverse this reaction whereby I'll have ammonia that is breaking into constituents atoms, or maybe constituent species which are forming it, I'll have the enthalpy illustrated as change in H positive 92.8. So reversing the reaction will have a net effect of changing the signs of that specific enthalpy. And for illustration purposes, this is going to have a net effect on the illustration for the energy level diagrams. So suppose I have this one for the first one, whereby I'll have, maybe for the second equation, this is ammonia that is split into nitrogen plus hydrogen. So the net change in enthalpy is going to be plus 92.8 kilojoules. Whereas if I have another graph for the same, for the reaction, so this is for reaction number, okay, let's say this is 1, 2, so this is for reaction number 2. So for reaction number 1, which is having a negative value, we're going to have nitrogen reacting with hydrogen to form ammonia. And always remember that these equations are stoichiometric. So, and we always encouraged for us to mention their phase or state, whether it's a liquid, gas, etc. So in that case, the net change in heat is going to be negative 92.8 kilojoules. So from thermochemistry, the effect of reversing those equations is going to have that change illustrated as such. So as such, of course, we have already exhausted and discussed about the enthalpy of formation that involve the formation and the breakage of our bonds for the reactants and formation of bonds for the new product, and how we can generally be able to illustrate it using the energy level diagram, using the examples we have listed on the board. So basically this is what is going to entail, and as we proceed, maybe we're going to use other examples, using specific examples to try and quantify what basically the enthalpy of formation, how the enthalpy of formation can be able to be achieved. So I hope we have understood this concept of enthalpy of formation as we have illustrated using the examples, and maybe if we come across a challenge that requires us to use the concept to be able to do it appropriately. So that is it for today, guys. Bye. God bless.